Okay. So today what I want to talk about is WeightWatcher and how WeightWatcher can inform what's going on in double descent. And to do that, we need to first have a little better understanding of what double descent is. So if you go back to the original research, the actual original double descent paper came from the theoretical physics literature. I gave the reference. I'll share this deck online when we're done here, called Linear and Nonlinear Extension of the Pseudo-Inverse Solution for Learning Boolean Functions. So basically what they're doing is applying linear regression to a binary classification. And when you apply linear regression to a binary classification, you get all sorts of interesting phase behavior. And to a physicist, that's really interesting. So this was actually originally explained using statistical mechanics. Then, many years later, let's see, 20 years later, 89, 30 years later, Belkin wrote this paper, which was like 5, 6 years ago, on reconciling machine learning practice and the bias variance trade off. And of course, what he's trying to do is he wants to understand why doesn't bias variance theory work? Pack learning theory, the bias variance stuff that machine learning people use doesn't work at all in this problem. And for neural networks, and people try what's going on here. And it turns out if you go back to the original physics literature, you can see some really interesting behavior. And then a few years ago, I wrote a blog on this. I decided, this is really interesting. I'm going to apply WeightWatcher to it. And it turns out WeightWatcher works out of the box. And I'm going to explain why. So if you think about why does pack learning theory fail? Right? This is usually how the computer science people present it. They have this model, you have the risk versus capacity, and this idea that you train there's this trade-off between the test error, the test risk, and the training risk. And you get this curve, and you're in this regime where you're underfitting or overfitting. And this, if you take any machine learning class and statistics class, they have this curve in plot A. And of course, what we've learned is that this doesn't work at all for neural networks. In fact, it doesn't work for linear regression either if you're in the over-parameterized regime. And that's what they realize. And so if you go back now they want to try to update the theory, say, well, if you're in this under-parameterized regime where you have more data than parameters, then, which is usually what you have in statistics, right? When you do statistics, I want to do a statistical sample. You need to have a huge amount of data to do a sample. That's what it means to do statistics. You compute the mean, you compute the variance. That's what statistics is all about. So in that regime, this works fine. But what happens is that when you have far more parameters than you have data, which is what's going on in neural networks, then you have this other curve they talk about where you're in this interpolation threshold where you got the training error to go to 0, and yet somehow the model is still able to work. It's in this interpolating regime where it's able to somehow, there's benign overfitting and you're able to get things to work. And this is the picture that people have been pushing for some time. And of course, this has a big implication because it means you no longer need to regularize, because this whole point of the capacity is that you're trying to control the capacity. So if you're training and your training risk goes to 0, if the capacity of the model is too large, the idea is you shrink the capacity of the model to prevent overfitting. So you use dropout. A dropout, for example, is your classic regularizer. Maybe use L1, L2 dropout. This is the whole idea. But when you're in the interpolation threshold, we don't need to control the capacity of the model anymore. The models can be as big as possible. And that's what everybody's doing. It's like, well, did you actually read Belkin's paper? If you read Belkin's paper, you would see he goes and reproduces the original experiment in the 1989 paper. And he says, if you look at the number of parameters divided by the number of weights, so I think this is like, if you plot this ratio, basically you depending on how you plot the ratios, you'll get this curve in the over-parameterized regime. And see, you're training to interpolation. This is the training error. And so they're interested in this interpolation regime where they think the training error goes to 0, but there's this weird spike. And they call this you'll notice that in this plot, the interpolation goes to 0 and the spike is at the interpolation threshold. But in the experiment, it's not quite there. So, theory and experiment already don't match perfectly. But they're interested in, wait a minute, where did this second phase come from? And what they forget is that, so they're interested in sort of, while there's this interesting behavior, but they forget that there are these, there is this curve that you get these minima. Actually, now that I'm looking, I'm not sure I got the minima right. But the point is that you get minima in these curves. Now, if you go back, if you actually plot, so the solution to this is to use WeightWatcher. And what I'm going to show you is that if you actually reproduce the 1989 experiment in the under-parameterized regime, if you plot the mean test error versus the WeightWatcher alpha, you'll see that the alpha just keeps getting larger and larger and larger as the test error gets smaller. So you cannot apply WeightWatcher in the under-parameterized regime. You have to apply it in the over-parameterized regime. And in the over-parameterized regime, if you plot the test error versus alpha, you would see, look at that, the test error goes down, down, down. Right when alpha equals 2, the test error is minimized, and as alpha gets larger than 2, it goes up again. And again, all I did here was take the original, and I'll go through, I'll explain exactly what I did in a few minutes. But what you're going to find is that the at alpha equals 2, you get this really nice power law. You can, so in this case, in the original experiment, the number of P patterns is 1/2 the number of features. Is that right? Yeah. And you get this, you have many more features than in other words, you have more features than data. So in this model, N is the number of features and P is the number of patterns, meaning the number of training examples. That's the old physics notation. And you'll find that when in this old model, when P is 1/2 N, you get a perfect fit. And the WeightWatcher alpha is exactly 2. And this is what I've been saying for some time, is that when you apply WeightWatcher, you can see that as alpha approaches to for a layer, that the model's actually, the test error is minimized. Notice the test error doesn't go to 0. It's just not very large. And moreover, you can even see some of this new theory, which is acetyl paper, the dead X condition holds also. So, you'll see that when you're in this over-parameterized regime and you're in the optimal part, this we call the operating part or the sweet spot, you'll see that alpha equals 2 and the dead X condition hold, which is the idea that the alpha equals 2 means that you can plot the spectral density of the eigenvalues, histogram of the eigenvalues, you can fit it to a power law with exponent -2. Or you can take the tail of the distribution and you can take the sum of the log eigenvalues, and the sum of the log of the eigenvalues will go to 0 if you normalize things properly. So what's going on here? Let's see what the original problem is and why this works. So in the original problem, what you do is you train a linear regression to predict the labels of a data set with binary labels. Now, if you think about what's going on in the layer of a neural network, what goes on, right? You have a layer, every layer in a simple neural network, like a multi-layer perceptron. You have the layer pre-activations, or WX plus B. That's a linear regression. And then you apply some ReLU function to it, which turns the outputs into either -1 or +1. It discretizes the outputs. In the traditional sigmoid version, you'd have something which is almost -1 or +1. So this original idea of applying linear regression to a data set with binary labels, this is a classic model for a layer in a neural network. We've talked about this a little before, but I'll let you think about that why this is a great, simple theoretical model for a layer in a classic multi-layer perceptron with a sigmoid activation function. And the idea is that what you're going to do is how do you set this up in an over-parameterized regime? It's actually really easy. You take N. N is the number of features, and P is the number of patterns. So you take N, and you get 2 to the N. You get 2 to the N features. So you form 2 to the N. Excuse me, 2 to the N patterns. And I think I have N and P wrong here. You take this regression problem where you form 2 to the N examples. So it's widely, the space is gigantic. You have this gigantic space. And what you're trying to do So you have all these vectors, which are just, they're of length 2 to the n. Each vector is of length 2 to the n. And you ask, I'm going to count the number of ones. And if the number of ones is positive, I'll label this vector as a +1. And if the number of ones is negative, the number of +1s is negative, I'll label this as a -1. So this is a classic problem of an over-parameterized, classification problem. So you think of every column in the vector is some parameter in the neural network. It corresponds to some parameter you're trying to learn. And so you have 2 to the n of them. So you have an enormous number of an enormous number of features in this problem. And so what you're trying to do is to classify, given some if I create some arbitrary vector, can I classify it as +1 or -1? And what you do is you train a model on some, obviously you cannot create 2 to the n examples. So you train it on some small number, you train it on n examples, and you try to predict what happens in this massively over-parameterized case. I hope that's clear to everyone. And so the idea is you set this up so that you can do this. You can run this as a linear regression, and you'll get some result. Now, the theoretical setup of this is fairly straightforward. If you want to understand this theoretically, well, and by the way, I'll just comment, I have a notebook. If you go to my blog, I have a notebook where I describe exactly how to do this, and it's all coded up, and you can try it yourself. But the idea is that, if you only have, you have just this massive set of parameters or features, and this is the classic example of an over-parameterized classification problem. So the way we describe this is we're going to try to treat this classification problem as if it were linear regression, which is typically a terrible thing to do in practice. So we're going to do the student-teacher setup. And in the student-teacher setup, you say, well, there's some true teacher vector. There's some true vector. And the idea is you have n training examples. Mu goes 1 to little n. And each x mu is drawn from a Gaussian distribution, which is massive. So you have this massive Gaussian distribution. And I'm sorry if the n and p's are a little different. But the idea is you have this massive distribution you're drawing x from. So these x mu's correspond to these vectors here. And the idea is that you want to find the ideal solution. So you can, for any solution, there's an ideal solution, a prediction. So again, if I'm here and I give you some arbitrary vector on this hypercube, and I ask, is it +1 or -1? There is some optimal solution. There's some weight vector. And you say y mu, which we call the teacher, the optimal solution, the training label, or the perfect label, is this optimal solution plus some noise. So this is a classic linear regression problem. And the way you solve it, typically you would see it as, I'm going to minimize the error between what is my prediction minus minus what I'm going to try to optimize for W, and this is my loss function. So we fit the vector to the training using ordinary least squares, that is, we minimize the sum of the square error. So by doing this, this is the teacher minus student. So this is a classic student-teacher setup. And the idea is, of course, you're trying to find the optimal W. This can be solved using pseudo-inverse. So in the old days, like in the 90s, the early 90s, the late 80s, you would say W is the pseudo-inverse, X transpose X inverse X transpose Y, where X is basically the data matrix or the design matrix. This is pretty standard linear algebra. The problem is that this thing is impossible. This is really, really hard to invert. It's massive. When I first started in industry, I worked for a company called eSelf. We were making a personalized search engine. And this is exactly what we did. I had this massive pseudo-inverse problem that I had to solve. This is literally what you did in industry. So you set the problem up like this. And then the question is, you want to compute the test error. So the test error is the expected value over all the data. So you take all the possible data and you average over this error, where you have the student, again, minus the teacher, where you know what W star is optimally, and you're trying to compute an average over X. This is a classic problem from statistical mechanics. And the question is, how do you evaluate this expected error? Well, if you evaluate the test error, this will give you the double descent curve. This is what you're doing. So, the idea is we find the expected value with respect to some sample over the data. And what you would find is that, in these simple toy problem, like, in this toy problem we've set up, where everything is isotropic, you would find that the test error goes as 1 over p times the norm w minus w star, plus some extra term of the noise. So if you want, I'm happy to go through and work out all the math. I prepared some notes to do that. But basically what I want to point out is that you're just trying to solve this expected value over the data. And you can do, and you do it usually in the large n limit. So you take the large n limit where n and p go to infinity, but you hold alpha is over p over n fixed. So the idea is that there's you hold this fixed. This is called the load. Now, the key here is that if you do like VC theory or pack learning theory, you're typically not holding this alpha fixed. By the way, this alpha is not the WeightWatcher alpha. This is just the load. So Michael Mahoney and I have a paper on this from 2015 where we discuss like why holding this fixed is very different than what's done in pack bounds or VC theory. Because you hold this fixed, you're in a different limit. You're in a different limit, you're going to get a different result. So this can be resolved. You're in the end, you're going to get a result which sort of looks like you can solve this problem by taking the average over x. And by the way, if you read the WeightWatcher theory paper, a large part of the WeightWatcher theory paper is explaining how to take this average. How do I take the average of a student-teacher model? Where the difference is, I'm going to generalize this to a matrix. But, you have this test error, and you're just computing the test error, right? And you can do this with a replica calculation. You can do this with a random matrix theory. I mean, you can just evaluate the X matrix. You can form the what's called the data sample matrix, the covariance matrix exactly using random matrix theory, or you can use WeightWatcher to do it. And you actually get the same result. You get that you can just get a very simple quadratic, a very simple form for the test error in terms of Q and P. I didn't explain what Q and P are here, but I'm happy to go through all the math if somebody wants to spend an hour or two going through that. But you can get a result for the test error, and what happens is you get a curve which looks like this red curve. So this is described in a paper by Opper called Linear. I'm happy to share it with you. Unfortunately, it's no longer online. Called Learning to Generalize. And this is a great paper, actually, if you want to understand the difference between statistical mechanics and statistical learning theory. But, again, if you run this experiment, here I run the experiment where I actually compute the mean test error for this hypercube problem we set up. And I do it in the over-parameterized and under-parameterized regimes. And here, this alpha is not WeightWatcher now. This alpha is the load. So this is the load, P over N. And if you do this, and if you do the theoretical calculation, you get the exact same result. And so Opera shows how to do this using a replica calculation. You can also do it by simply, you compute this matrix, you take this data matrix X, and you just solve for the spectral density of this object directly. So you form the covariance matrix, and you solve it using random matrix theory. And what you would do is you say, well, typically you would model this object, X transpose X, as a Wishart matrix. So if you were computing this as a random matrix, if X is random, this object inside is called a Wishart matrix. And when you invert it, it's called an inverse Wishart matrix. And if you read the Seidel paper, you get to the section where I discuss the models of the R transforms. You'll see we use the inverse Wishart matrix as a model for explaining the theory behind WeightWatcher. This is really important to understand. So we're going to look at the eigenvalues of this matrix. So again, if I were computing, go back and I find it, this expected value, what I'm doing is I have to compute the spectral density of the data matrix. And then I would be able to evaluate this integral by knowing its spectral density. And again, it's a straightforward calculation. Well, it's not straightforward. You can do it. So what happens if you actually look at the spectral density of that matrix? Well, I kind of zoom in. I should put this in different order. If you look at the spectral density, I'll put this in different order. If you look at it, the data covariance matrix, I call it H. If you compute it for a random matrix, it looks like when n equals p. So when we're at, I should do this correctly. When we're at this region, which is this phase boundary, N equals P. So you have exactly this. So N equals P. You're in an overfit regime. And what happens is, if you compute, this actually is this is a standard Marchenko measure. This is a Wishart model. And what happens is, because N equals P in the Marchenko-Pasteur distribution, the number of zero eigenvalues explodes. So it just, in theory, this thing is unbounded. So there's a huge number of zero eigenvalues here. And so again, the load is 1. If you invert this, when you invert this, you get this really, really long tail. So in WeightWatcher, you can actually do this. You can just input the matrix and you say inverse equals true, and it will compute the spectral density of this inverse. So you get this really long tail. So this makes the inverse ESD power law with alpha much, much less than 2, and that indicates the layer is overfit. So this is a classic inverse Wishart model for the load equals 1. So you realize there's a duality between the data matrix and the weight matrix. And this is something that I think one of Michael's postdocs has done some huge amount of analytic theory on this, explaining that there is this duality. But it's very simple to see. So you have lots of zero eigenvalues. So in other words, the data is very, very weakly correlated. And when you have weak correlations, if they're present, you get this long tail. And that's why when you have this, that's why you get this weird bump at N equals 1, which again, you would see, if you go all the way back to the statistical learning theory, this peak here at the interpolation threshold occurs when N equals P. Now, it turns out when you're here, however, when you're at this point, for reasons that are non-trivial, it turns out when you're right here, it turns out you get a perfect power law with alpha equals 2. This is a highly non-trivial result. And again, I have this very long theory paper which tries to go into some of where this is coming from, using, again, the student-teacher model and analyzing the student-teacher model using renormalization group theory. But the idea is that the theory predicts right in this double descent curve, right in this over-parameterized regime, there is an operating point where alpha equals 2. If you go back and read the original HTSR theory paper, which we published in 2021, I think, you'll see that we talk about these universality classes of random matrix theory. And there's this underfit class, there's an overfit class, and then there's ideal class. It turns out there's actually another universality class right here at mu equals alpha equals 2. I don't bring it up in the paper, but if I can show you in the literature, in the theoretical physics and econo physics literature, they do discuss this idea that there's this perfect class here, which corresponds to the phase boundary between these two universality classes. So the point here is that the HTSR universality classes can be used to describe the inverse covariance matrix of the data, which is what's going on now because this matrix turns out to be heavy-tailed. This is why it works. And again, you can solve for these problems. Again, you can solve this actually exactly. You can get this curve exactly by doing an exact random theory matrix calculation, meaning that if I assume I can compute the spectral density of these eigenvalues, assuming the data is random, and then I can compute in the perceptron model, I can actually compute this expected error, and you'll get this curve. So this is sort of the highlights of what's going on with WeightWatcher. One of the kids in the gym made this funny thing to show, why does statistical learning theory is wrong because it doesn't explain double descent in the over-parameterized regime. And the point being that it doesn't. Statistical learning theory is widely focused on. You can find the plot. It's widely focused on this area out here, and not in this sweet spot. So in other words, it's. And the point, of course, is that so statistical learning theory is very concerned about this region here. But if you think about when you train a model as a practitioner, you're never here. Like, you don't want to be in the area where you're totally overfitting your data. Nobody wants to be there. Where you want to be is here. You want to be in the sweet spot. So if you're going to make a theory for people to use, you should make a theory that describes the region where practitioners actually live. And practitioners don't live here. In other words, they don't, they live in the sweet spot. And unfortunately, the existing statistical learning theory doesn't tell you anything. All it tells you is that make the models bigger, make the models bigger, make the models bigger, everything will work out. And you can see that that's, to some extent true, but it doesn't give you any guidance. And sort of the point of Weight Watcher theory is to say, no, what you want to do is actually realize that there is this sweet spot, and you can find the sweet spot using the tool, using some very simple adaptation of random matrix theory. So that's sort of the talk. I'm happy to go into. I prepared a slide, a PDF really that goes through all the math. If anybody wants to go through and do the replica calculation or do the random matrix theory calculation, I'm happy to do that. But I thought it would be better first to just go over the general theory and give you an idea of what's going on before we, dig into 3 hours of statistical physics. So I'm going to stop there. Does anybody have any questions? I'm happy to open the floor to questions.
Yeah, thanks for the talk,
Sure.
Charles. Appreciate it. I'm always curious to kind of gain an intuition for kind of some of these more foundational principles, and particularly when you mentioned that, like, a lot of this theory kind of revolves around the concept of performing linear regression on binary classification. So much of that just comes down into like the data that you're training it in and how you're performing all of that. Which
yeah, go ahead. Yeah.
Well, no, until the data set, or
well. The idea, what I'm trying to point out here is that, if I have any neural network. So I don't think I have a plot of this. I had it before. Let me try to find it. In any neural network has a. Oh, I turn my camera. Any neural network has an internal layer, right? And that layer is, usually, let's not worry about attention models, which are more complicated. But in a simple layer, linear layer, what is the layer it does? It does WX plus B, where X is the data, and you say, I'm going to take the weight matrix time to data, WX plus B, and I feed it through the activation. So in the simple model, the data is just random, right? Just random data. The point of WeightWatcher, the theory of WeightWatcher, say, well, look, obviously you don't train on random data, you train on real data. So what you want to do is you want to compute the spectral density of the real weight matrix. So instead of computing a random matrix, you look at the real weight matrix. And the point, what's the amazing thing is that there are these universality classes. So even though you have real data, it turns out that the spectral density of the weight matrix satisfies these universality classes. So there actually is a theory behind it which says even for real data, in the infinite limit, the real data, because the data is correlated. Remember, whenever you train a model, you're not ever training on a random data. The data's correlated, right? That's the whole point, is to learn the correlation of the data.
Yeah, there's actually a pattern there.
yeah, of course. And the point is that it turns out that these universality classes work for correlated data, even when it turns out it works really well. And that's somewhat surprising that it does this, because there's nothing in it's the theory doesn't distinguish between correlated and uncorrelated data. When you look at the eigenvalues, the eigenvalues don't know if they're correlated or uncorrelated. They're just the data. They're just eigenvalues. So this is sort of the magic of random matrix theory, is that you can apply it. You can apply it even in situations when the data is correlated, and that's the argument that I'm trying to show, is that, when you solve this problem, I compute the expected value, and I do it over, I assume X is an IID variable, Gaussian IID, and I compute the Wishart matrix, and then you evaluate this integral, and you get the result. And it turns out that because of the magic of random matrix theory, the result works for correlated systems as well.
And is the magic of random matrix theory essentially just your perturbation across your full spectrum, and attempting to
no, it's much more subtle.
Perturb features within the data set, or
No,
Hmm.
it's much more subtle. It turns out that, so I have a long paper. I have like a 120-page paper. I go through this, but this idea that what happens is in these models that you can think of each layer as satisfying a fixed point solution. So I can find a copy of this. And so as the layer is, we think of training a model, we think of the model as satisfying a fixed point solution. So in my theory, what I'm saying is that the actual let's see if I can switch the actual layers themselves. And I can't switch it. The actual layers themselves satisfy a fixed point solution, and that fixed point solution is, so the idea is that, let me see if I can copy this. I think I can do it like this. Give me a second here. I think this will work. I just trying to change the screen. Yeah, yeah. So as the model is training, you see that as the model is training, you see these perturbations that come out of the spike. That's what you're asking, right? You have a random matrix theory, and you see perturbations coming out, right? That's what you mean by the perturbations.
Yeah.
Right. So, I'm plotting the spectral density. I'm
Yeah.
training. These large eigenvalues start to pull out of the spectral bulk. Then they actually form a heavy tail. And that's not a perturbative thing. And so what's happened, and fundamentally it's not perturbative. That would be my argument. Is that you're basically, as the layer is training, it's undergoing a kind of, as it goes through backprop, it's going to approach a fixed point. And that fixed point is described by something called renormalization group. And so fundamentally in physics, so I can find it here. Renormalization group, there's a renormalization group equation, and that is fundamentally non-perturbative. Let me see if I can get all this. I get the whole thing. So there's a set of equations that it satisfies, and there's sort of this renormalization group equations, which represent a measure transform or a scale invariant transform. You can see
It's
this?
kind of like we're taking, so each layer is essentially.
Go ahead. I can't hear you.
Yeah, yeah.
Each layer, it's in my
yeah, I can see it. I
yeah,
can see it.
in my theory, the idea is that each layer has its own fixed point, and what happens is as you transform from student to this is a transformation from student to teacher. So we didn't go through all the math, but the idea is that you have this student matrix W or S, and this becomes S transpose. So I can do it here. I can't quite get in the. Here we go. This A is SS transpose. I don't have that. I'll just put a star here for transpose. Hey. This becomes SS. This S becomes SS transpose. And what happens is as you transform from an uncorrelated to the correlated components, there's this measure. There's this scale invariant transform that occurs. So this H, well, we won't talk about the whole equation. But the idea is the theory predicts that you should have the product of the eigenvalues, or the sum of the log of the eigenvalues of this matrix, which we called X above. They're all the same notation. Sorry. There's some technical reason for having them named differently in the paper, but this matrix, which we called X inverse, this was X inverse above. This thing is X inverse. This thing satisfies trace log. So this object here, the inverse, this H, I guess here we called it H. I'm sorry, we didn't call it X. This H is the A is the inverse of H, and the inverse of this matrix, the eigenvalue inverse, satisfy this trace log condition, which you can see here in this plot. So if I compute these eigenvalues, which are the eigenvalues of the weight matrix, or the eigenvalues of the inverse Wishart matrix, they satisfy this trace log condition. And that's fundamentally non-perturbative, because of this scale invariant transform. Because when you take this idea of you have to take this limit, and when you take the limit, in the limit you're no longer perturbative. You're so far away from the perturbation treatment. But this is the idea. This is very, very. I'm happy to go through this. It's very technical, but this is essentially what's happening. Is you have this idea that the fact that this inverse Wishart matrix you can use it as a model for renormalization group, And in fact, you get these two conditions, that alpha equals 2 and the trace log is 0. Does that help?
Yes. Yes, thank you.
There's a lot going on here. So, it's a lot going on. So it's okay that it's not obvious. I mean, there's a reason why this paper is 120 pages and it still could probably be 200 if I, there's a lot of, in some sense, it's very simple because you just say, well, I have a fixed point and you satisfy the fixed point and the fixed point. This is the fixed point equation. Why in the world this is a fixed point? Why in the world it satisfies this? You can derive it from first principles to some extent. But the main point is that it works even on these toy models. So it works for some non-trivial reasons. But it does work. And what I want to get across is the sort of my take on the theory. My argument is that in the over-parameterized regime, when you're here, there's more structure here. There's structure that people ignore, and they ignore the structure because they're thinking about it from a pack learning theory perspective. If you think about it from a statistical mechanics perspective, you actually can see the structure. And you can see the structure, and even in the simplest model. In the simplest models, you see that there's this structure. And if you take advantage of it, my argument is that you'll get better models.
And this is the full round trip here is this should not only will WeightWatcher help you tell where you fit is, but particularly how close you are to having the right fit.
Right.
And eventually where you're being able to scope your training.
Right. The idea is that for every layer contributes some bit to the error, or some bit to the accuracy. Depending on which error 1 minus error. Right. Every layer contributes to it, and the idea is you want to minimize the error for every single layer. And if you minimize the test error for every single layer, in principle, you should get a better model. It might hallucinate more. I can't guarantee it won't hallucinate. That's another. But in terms of out of sample performance, it should perform generally better. The idea it would do better. Yeah, that's the conjecture. And the idea, and so rather than just minimizing the test error for the entire model, this allows you to effectively minimize the test error contribution for each layer.
I think there's a question in the chat about going through the derivation.
I'm sorry. I don't see that. What is
E sub x?
You want to go through the derivation? Okay.
Sure.
I don't see it. Thanks. I don't know how I don't know how to use the chat. Because I'm using this OBS thing. Let me see if I can open up the derivation.
Oh yeah. No worries.
I'm happy to do it. It's going to take some time. Where I'm trying to find it. I have to change windows. So give me a second here to change what I'm sharing. First I have to get to it. Just give me a second. Here we go. All right. Let me see if I can. All right. Let's see if I can change the window sharing. Give me a second here. Sharing screen. I'll stop the. Let's see. Stop. No. Stop streaming. No. Make selection. Share this window. Okay, can you see this?
Yeah.
All right.
So this is your replica. This is your replica PDF, right? The one that you shared a couple of weeks ago.
Yes, yeah. I shared that. Did you want to go? Did you have some questions about that?
Maybe you can just skim through it.
I'm happy to. Just give me a second, okay? Here we go. Yeah. So the idea is that I'm this is what I took results from. This is I put together I vibe coded this, so as they say, but I kind of went through and tried to put together a sketch of what this looks like. So the idea is that we want to understand. Again, this is sort of the idea. If you have this student-teacher model where you're trying to compute the error between what is effectively the teacher, which is the label, and the student. And by the way, I'll comment, when you read the CETL paper, I take the labels out of the error functions. And the reason is because typically you if the student is ideal, well, then obviously you know what the label is. The label is in terms of the pseudo inverse. So in a replica calculation, what you're going to do is you're going to define a partition function over the energy. You're going to take the average log z over the data, and then you're going to take the limit as beta. You're going to take a limit. I think it says beta goes to 0. I believe it is beta go to. I always forget which limit we're in. Let me double check it. You take the limit as beta goes to. Well, I'm pretty sure it's. I'm sorry, I don't have it. I'll just go through it. I'll go through it as we go through. You take the limit to get rid of the idea of beta. Beta is the regularizer. So in statistical physics, the idea is when you compute generalization errors, you don't compute generalization over a distribution function. You ask how does this log z is called the free energy, and you ask how does it change with beta, or the inverse temperature, where beta is 1 over t. Yeah, oh, here it is. Take the beta goes to infinity, so t goes to 0, right? So the idea is to solve the problem. What you do is you write down this function z, you compute average log z, and then you take the limit as beta goes to 0. Beta goes to infinity, and that will give you the actual average energy. And you can work through, you can convince yourself that that's correct. In the CETL paper, I derived some of this and kind of show you how to derive things like where does the average energy come from. You just have to kind of work through these partial derivatives and convince yourself of this. But the idea is you're going to compute the average of this object. And the problem is you can't compute log z. Because you're going to compute log z. Instead, what you do is you compute the limit as k goes to 0 of the average of z to the k minus 1 over k. So this is called the replica trick. This was the idea of using replicas was first, I think, proposed by my graduate advisor's postdoctoral advisor, Sam Edwards, and then solved by Parisi, who won the Nobel Prize. So the idea is you take k, so you have to evaluate this object. So you're going to evaluate average of z over the data, because you can't evaluating average of log z over the data is basically impossible to do. So you take this object, which is z of k, and you're going to write, you have k of them. So you express this in terms of a product over k, where you have basically the integral now over each weight vector. Each weight vector is a replica. So you have to make these replicas of the weight vectors. And so you basically, it's almost like training the model over and over and over again with different initializations. And then taking the product of all, and then taking the limit as the number of replicas goes to 0, which is in physics, in math, it's called an analytic continuation. So this is a very, very technical thing that you need some complex analysis to do. But the idea is you make replicas of the solute. You make replicas. So imagine if I were to train the model and over again with different initializations. And the point is that you generally should get something very similar. And if you were to train a model twice with the same initialization and the results were completely different, something would be wrong. And that typically means you've overfit your data. So now when we write the average of this, we write the average over all the data matrix, times the noise, and some average over the noise of the problem, times some distribution. This is the distribution of the data and the noise, times this product. So this is what, and for each of these WAs. So we're going to compute this object, and the goal is to compute this. So you have to be able to write down these measures. So again, X is an n by n matrix, E is Gaussian noise, and the ideal teacher vector this is the actual equation for the vector, which is written in terms of the pseudo inverse. So you have to evaluate this integral, and so in random matrix theory, if you could write down this measure directly, if you could write down d of x directly, I assume you can see this. If you could write this down directly, you could just do the integral, right? And so if you assume this is, and so there's another calculation where you just do the integral correctly. In a replica calculation, what you do is you have to first break down the error into, you have to take this error and break it down in some quadratic form so you can express it in terms of what are called overlap parameters. So you take this is the original expression, teacher minus student squared. I substitute in the optimal teacher vector plus the noise. I write down the expected value. I then put it over all K. I get something that looks like I get this nice expression. Then I want to average over the random design matrix. So this is your measure. X is a matrix and it's assumed to be Gaussian. So the measure is given minus P over 2 trace XX transpose. So this is a Gaussian measure over a random matrix. And so this is your measure. So this is the object that was here.
Sorry, is trace of X times X transpose your cheap X inversion?
No, we're not going to invert it here. Here we're gonna. This is in the replica calculation. We're going to do something a little different. So what we do is we have to expand. You expand X in terms of the little x's, like this. And so you stick it inside. So you stick the X inside. So you have this thing, this error. We haven't done the X yet. You put the error. You expand it in a quadratic form like this. And then what happens is you do something called a Hubbard-Stratinovich transformation. So you have to take this quadratic form. A Hubbard-Stratinovich transformation lets you. It's basically complete the square. So you take this quadratic form and you effectively linearize it by introducing field variables. So again, this could take like 2 or 3 hours to explain, but the idea of there's a decoupling. So this is a standard problem. It's a standard trick in physics where you can convert a quadratic form to a linear form by introducing a field variable. So you integrate over X.
Complex conjugate, or is that like? Sorry for interrupting.
This W star is the optimal solution. So this is.
Okay.
Where was it? It's this object. It's the pseudo-inverse solution, right? So this is the pseudo-inverse solution. So that you assume the teacher is almost perfect and has a little noise. So this is the teacher label.
Okay.
All right. And the idea is that you have this decoupling step, which is you're able to write this exponential in terms of an integral over this. Now you have this is the K. You have this variable A. And you're able to do this transformation where you get this extra Z term. So this is basically this Hubbard-Stratinovich transformation lets you represent the quadratic form. It linearizes it. See, it linearizes it in terms of a field variable that you're going to integrate over. So this is a standard trick in physics that you can convert a quadratic form into a linear form by introducing a field variable. And the idea that, and then you integrate over and so this is something that we could probably spend an hour going through like where this, but this is basically like completing the square. So you can now integrate over X row by row using its Gaussian measure. And so the idea is that this object now, because you have this, you've done this expansion, allows you to define these overlaps. So now you have overlaps in replica space. So once you've done the expansion, you get these terms like QA is 1 over P WA squared, or QA, and then QA. So this is the QAB is the replica between them. And M is this. You get these various parameters, which are going to stick into this equation. And what you do is, because you have K of them, you have to make some assumption about how one replica is related to another. And what you do typically is just say, well, everything is isotropic and uniform. So you just assume that, everything's constant, right? So this becomes a constant. QA becomes Q. MA becomes M. Where A is the index of the replica. A and B are the index, and QAB becomes Q. So this is called replica symmetry. So the idea is that even though you have these A's, even though you have K replicas indexed by A, all the replicas are basically identical for all practical purposes. And so their couplings are, if there's a coupling between them, that coupling is just a constant. And so you end up making this assumption, and then you solve this integral using something called a saddle point. And so you're going to end up with an expression of Z of K, which looks like some integral over a bunch of variables. So when you do the substitution, you substitute in these variables, you do a change of variables, and these change of variables, now you're integrating over these parameters. So instead of integrating over W, you integrate over the replica parameters. And that's the idea. You do a change of measure. And this change of measure lets you write you're going to be able to write z of k in an exponential form where this depends on n. And then you solve this using saddle point, meaning I assume that I can replace the integral in terms of n with its peak value. And you get these saddle point equations where whatever expression you got for this psi now becomes d psi dq is 0, d psi dm is 0, d psi dq is capital Q is 0. If you read the Seidel paper and you go through it, I actually go through all of this, but the only difference is that instead of doing a replica, instead of using replicas, I actually treat the overlap matrix, this object, these are matrices, and this object is the correlation matrix. So instead of doing a replica, what we do is we treat it phenomenologically. But it's very, very similar. So if you read the paper very carefully, it explains what these calculations are, and you'll see exactly what's going on here in terms of you understand what is a saddle point, why you take the large n. So it's a very similar calculation, but there is this idea that, I'm trying to change variables so that instead of integrating over w, find the integrate over w, instead of w, I can integrate over these q's, over the q's and the m. So I change variables, which gives me this solution, and then the saddle point solution actually gives you this final form for the test error. That's the sketch of the idea. I didn't go through the actual change. Next time, happy to work this out and go through all the change of variables and show you. It's very technical, but it's totally doable. And you'll get this final result. And then the idea is you take the limit. There's no the whole point of double descent is that there's no regularization. If there's regularization, there's regularization, the inverse matrix doesn't explode because you regularized it. So the idea is you take beta goes to infinity. So when beta goes to infinity, you end up with the double descent problem. In WeightWatcher theory, you take beta goes to 0. You're in a high temperature limit. So you're in the limit of very, very strong regularization. So the idea being that if you regularize things properly, in other words, use WeightWatcher as a regularizer, you'll get the WeightWatcher result. But in here, you take the limit as t goes to 0, which basically removes the temperature dependence of the problem, and you end up with this finite, you'll end up with the actual final solution. And you get something like this. So generally, and so we write them. So does that help? I kind of sketched through it. Did you have some specific questions that I can answer now?
Yeah, well, I'm just, I was asking mainly to really understand the difference between the limit of n and p going to infinity with this linear correlation between them and the limit that the tangent kernel people do.
The problem, I don't know what anybody else does because I don't read their stuff. So I wish I could answer, but you would have to tell me. I've actually never read any of those papers. I mean, I know statistical physics, so when I worked out the WeightWatcher theory, I just worked out a statistical physics theory. I published with a guy at the university, so my always position has been, it's his job to go and figure out, what his colleagues are doing and explain it to him. I wish I could give you an answer, but I just have no idea what they're doing. My general impression is that, my understanding of it from listening to one of Greg Yang's talks is that their limit is in a limit where the system no longer learns anything. That's useless. So if you're in a limit where nothing can be learned, the theory is in the wrong. You're not in a limit where people are actually doing things. So I'm sorry. I mean, maybe you could give us a talk on NTK and we'll try to figure it out.
That sounds good because I do know more or less the theory behind it.
Yeah.
So I can probably organize some slide deck or something.
That would be great.
Does it work for next week?
Yeah, that'd be great.
Same
I think
time.
so. I might have jury duty next week, just to warn you. So I got called in. Hopefully I won't, and we can do this. If it does, we'll do it the week after.
Okay, good.
Yeah. So again, for me, it's when you look at double descent, you're just you're evaluating this average, right? You're just evaluating this average. That's all it is. So if you evaluate the average in the right limit, In random matrix theory, you also take the limit as you retain the limit of the matrix being, you don't let the matrix become too rectangular, right? So the matrix you're always in the limit of n over m being fixed. So when you do random, you have this matrix, like you have the X matrix here. Where is it? This X matrix, which is the data matrix, right? It's this way, it was defined way up here. This thing, you're always in the limit where this thing, like when you scale it up, it doesn't become too rectangular in any dimension, right? It retains its aspect ratio. And my impression of these things that people do is they'll take like a large n limit or a large m limit, but they take a matrix like this and they make it super rectangular, and that's not a useful limit, because it's not the physical. You're not describing the object in a way that when you take that limit, it everything washes out, so you lose the structure. And my impression of what goes on in many parts of statistical learning theory is they take a limit where all the structure gets washed out, so you don't see the minima. It's just not there because it's not there in their limit. It's just like taking a bound. If I take a bound that's vacuous, all the structure goes away because you have this vacuous bound. But I just don't know the NTK. So yeah, that'd be great. I would love to see it.
Yeah. Okay. Good.
Any other questions I can answer?
I have a question. Why did we choose the data as identity? I mean, as Gaussian?
Oh, everybody does it. It's because you can. In these theories, you have to be able in field theory or statistical physics, you choose things to be Gaussian because you can evaluate Gaussian integrals. That it's a standard. It's what the theory uses. It's very hard to
Did we
deal with
use it
like
anywhere in the?
Go ahead.
Did we use it anywhere in the proof
In here?
or the?
Yeah, in here you do use it. Yeah, I mean, I haven't gone through the whole example, but you use the idea that these are Gaussian variables when you evaluate these integrals. Everything. It's the same reason you take the squared error, because it's easy to evaluate.
Okay.
We have to go through you have to go through the whole. I'm happy we have to do this again. Go through every single detail. If you read the Seidel paper where I derived the WeightWatcher theory, you'll see exactly where you have Gaussian data, you get a Gaussian integral, and then you evaluate the integral, and you get something called a functional determinant, and that's why you do it. So here I'm just kind of sketching through this today, but absolutely everything here, the data is Gaussian. That's an important aspect. The fact in random matrix theory, though, like in the stuff with WeightWatcher, that's sort of the idea is that the universality classes apply even if the data is not Gaussian. That's why we do it. Right? You can apply WeightWatcher to non-Gaussian systems because you have these universality classes of the eigenvalues. And the eigenvalues that it doesn't depend. In fact, it's explicitly is for systems where the data is non-Gaussian. That's actually what it's treating.
Got it.
Okay. All right, so that's about an hour. If anyone has anything else, I'm happy to hang out, but I'm going to stop recording.